Assalamualaikum and good day everyone. My name is Nur Syamimi Alia binti Nazri, and today I'll be providing a comprehensive overview of the key chapter from our Physics 568 course. This presentation will delve into the fundamental concept and principle that form the backbone of our study in this subject. For this semester, we focus on 5 essential subtopics. In the next slides, I will summarize the core concept of each chapter to make them easier for us to understand. The main concept here is that charge can accelerate and move with different velocity as described by Maxwell equations, like charge repel and opposite charge attract. Charge can be positive or negative, measured in the coulombs, with the smallest unit being 1.602 times of 10 power of negative 19 coulombs. Charge can be conserved. Electric flux has a positive divergence for flux out and negative for flux in, with the higher flux density indicating a strong electric field. Field lines do not cross. It is parallel lines show a uniform field, and converging or diverging lines show a non-uniform field. Coulomb's law states that the force between the two charges is proportional to their product and inversely proportional to the square of their distance. Magnetic fields are produced by current and permanent magnet as well as in a solenoid or coil. Maxwell equations separate into two pairs, which is the electric flux density with electric field intensity in the Coulomb's and Gauss law, and the magnetic field intensity with magnetic field strength, which is in the Biot-Savart and Ampere's law. Moving charges create electric current, which produce magnetic field line around them, with electric field direction perpendicular to the magnetic field direction. Next, Chapter 2, Vector Analysis. Unit vector which have a number units represent a direction by dividing the vector by its magnitude. Position vector can give a velocity and distance is formed using a magnitude, while vector distance uses the distance vector. The dot product or scalar product of a two vectors is 0 if they are orthogonal. One is parallel and negative sign if they oppose each other. The vector product, which is a cross product of a vector A and B, result in a vector normal to both A and B with a times B equal to 0 if they are parallel. This product also represents the area of the parallelogram formed by the vector, following the right-hand rule for direction. The triple product finds the volume of a shape. Vector component can be projected parallel and perpendicular to another vector. A scalar field assigns a scalar value to each point, while a vector field assigns a vector with magnitude and the directions. Cartesian coordinate use x, y, and z direction, while cylindrical coordinate use rho, phi, and z direction, while spherical coordinate use r, theta, phi direction. These coordinates have their specific range and transformations. Vector calculus using a Maxwell equations involve operations like divergence, line integral, and partial derivative. The gradient finds the scalar field directions of charge. Divergence calculates a scalar field flux using the divergence theorem, and the curl measure rotation, determining the calculations using a Stokes theorem. Next, Chapter 3 of a static electric field explains the basics of the electrostatics, starting with the idea of electric charge, which can exist as point charge, line charge, surface charge, or volume charge, each with its own density. It covers Coulomb's law, which describes the force between the two charges. The electric field at a point is the force per unit charge, with a field line showing the directions from the positive to the negative charge. For continuous charge distributions, the electric field is found by integrating over all charge elements. Gauss' law helps calculate electric fields in the symmetrical setup by relating the total electric flux through a closed surface to the enclosed charge. The potential is the work needed to move a unit charge between the 2 points in an electric field, and it's used to determine the potential energy in the charge distribution. Current density, which is the current per unit area, is linked to the electric field through a material's conductivity. This is a summary for the static magnetic field. Magnetic fields are produced by a permanent magnet like Al-Nico and governed by a Biot-Savart law and Ampere's circuit law. Biot-Savart law, similar to the Coulomb's law, describe the magnetic field from a steady current and allow calculations of the magnetic field at a point due to a current element. The magnetic field intensity for the line current and other configurations like circular loops and solenoids can be derived using this law. Magnetic flux density is measured in a Weber per square meter or Tesla, and unlike electric flux line, magnetic flux line from closed loop. Maxwell's equations explains how electric and magnetic fields are generated and interact. Magnetic scalar potential is used in a region with a zero current density and satisfies a Laplace equations, while vector magnetic potential describe a magnetic field in a more complex scenarios. Magnetic force on a moving charge or current carrying conductors are described by the Lorentz force law. Current loops in the magnetic field experience the torque essential for the operations of devices like DC motor and generator. For the last chapter, it explains the difference between the static and dynamic electric and magnetic field. Static field come from stationary charge and steady current, while dynamic field come from a changing current or accelerated charge, leading to the electromagnetic wave. Faraday law say a changing magnetic field in a circuit creates a voltage EMF that causes a current opposing the change in the magnetic flux, which is that in the Lenz's law. There are the three types of EMF. First is transformers EMF from a stationary loop in a changing magnetic field. Second, motional EMF from a moving loop in a static magnetic field, as in a generator and motor, and the EMF from a moving loops in a changing magnetic field. Maxwell's equation describes how electric and magnetic field interact and propagate. A charged particle in the electric field accelerates linearly, while in a magnetic field it moves in circles or spirals depending on its angle to the field, a concept used in old TV and computer monitors to form the image. That's all from me. Thank you for watching.